What if I told you everything you thought you knew about electricity is wrong? We all learn it in school, right? Close the switch, the circuit is complete, and electrons start flowing through the wires like water in a pipe, powering your light bulb. It's a simple, neat picture. But what if that picture is fundamentally misleading? What if I told you the energy that powers your life doesn't actually travel inside the wires? Mind-blowing, isn't it? But stick with me, because today we're going to uncover one of the biggest misconceptions in physics. The truth is much weirder and way more fascinating. The real action isn't happening inside the copper. It's happening in the space around the wires. To understand this, we need to think about what energy really is in an electrical circuit. It's not the electrons themselves. The electrons are just the workers, the messengers. They drift incredibly slowly, slower than a snail's pace, bumping into each other along the way. If we had to wait for them to travel from the power plant to your home, it would take years to turn on a light. So, what delivers the energy almost instantly? The answer lies in fields, specifically electric and magnetic fields. These two fields are the real superstars of the show. When you connect a battery to a circuit, it creates an electric field that stretches through the space around the wires. This electric field points from the positive terminal to the negative terminal. At the same time, the moving electrons, even though they move slowly, create a magnetic field that circles around the wire. Now here's the magic. Where these two fields, the electric and the magnetic, exist together, they create something called the Poynting vector. You can think of the Poynting vector as an arrow that points in the direction of energy flow. And this is the crucial part. The Poynting vector, the flow of energy, points from the space around the wires into the components that use the energy, like the filament of your light bulb. Let's visualize this. Imagine a simple circuit, a battery and a light bulb connected by two wires. The battery creates an electric field in the space between the wires. As current flows, it creates magnetic fields looping around each wire. Now, if you use the right-hand rule of physics, you'll find that the direction of the energy flow, the Poynting vector, is parallel to the wires but in the space between them. The energy is being guided by the wires, not flowing through them. The wires act like rails for a train, but the train itself is the electromagnetic field traveling in the space alongside the rails. So, the energy leaves the battery, radiates out into the surrounding space as an electromagnetic field, travels through the space near the wires at nearly the speed of light, and then converges back into the light bulb to be converted into light and heat. The electrons inside the wire are just responding to this field, jiggling in place and dissipating a tiny fraction of that energy as heat. The vast majority of the power is delivered through the field. Think about it like this. A river isn't just the water. It's the riverbed and the banks that guide the flow. The wires are the riverbed, but the energy is the water flowing in the channel they create. Without the guiding structure of the wires, the field would just radiate out in all directions, like the signal from a radio antenna. This concept was figured out by John Henry Poynting way back in the 1880s, but it's still not how most of us are taught electricity. Why? Because the water in a pipe analogy is good enough for most practical purposes. For an electrician or an engineer designing a simple circuit, calculating current and voltage using Ohm's law works perfectly fine. You don't need to think about electromagnetic fields to know what size wire to use. But when you start dealing with high-frequency electronics like in your computer or your smartphone, or with radio waves and antennas, this field-based view becomes absolutely essential. It explains how energy can be transmitted wirelessly. A radio antenna is essentially designed to launch this electromagnetic energy field into space without any wires to guide it. Your phone's antenna is designed to catch it. It's all the same fundamental principle. This also explains why when you flip a switch, the light turns on almost instantly. It's not because electrons race from the switch to the bulb. It's because the change in the electric field, the go signal, propagates through the space around the circuit at nearly the speed of light, telling all the electrons along the path to start moving and delivering energy to the bulb almost simultaneously. So the next time you plug in your phone or turn on a lamp, take a moment to appreciate the invisible reality. You're not just completing a circuit, you're orchestrating a dance of invisible electric and magnetic fields, commanding a wave of pure energy to flow through the space around you to power your device. The wires are just the stagehands guiding the real star of the show. The energy isn't in the wire is in the energy field. It's a beautiful and profound shift in perspective, reminding us that the universe is often more complex and elegant than our simple models suggest. The invisible world of fields is what truly powers our modern lives. Thanks so much for joining me on this deep dive into the true nature of electricity. If this blew your mind, hit that like button and be sure to subscribe for more videos that challenge what you thought you knew. Let me know in the comments what other physics misconceptions you'd like me to tackle next. See you in the next one.